Okay, section 2.5 is the fundamental theorem of algebra. With the fundamental theorem of algebra, it pretty much tells us that for any polynomial to the nth degree, we have precisely n linear factors. So if I have a quadratic, you guys know if we have a quadratic equation, such as x squared plus 4x plus 3, we can factor that into x plus 3 and x minus 3. That makes my zeros -3 and -1. And I can draw my parabola. It's a positive a here, so my parabola goes uphill and has those two zeros. Now, if I have a function like this one that I cannot factor, I don't have two factors that multiply to give me 5 and add to give me 3, so I'd have to go to the quadratic formula. Well, using the quadratic formula, I would end up having a complex number. So we'd have -3/2 plus the square root of 11i and minus the square root of 11i. That leaves us with two complex numbers, zeros. So this quadratic function does still have two zeros. They just happen to be complex zeros. Okay, for another example problem, I cannot factor x squared plus 10x plus 23. There's not two numbers that multiply to give you 23 and add to give you 10. So we'll use the quadratic formula, which x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Simplifies to -5 plus or minus the square root of 2. That leaves our linear factors being x plus -5 square root of 2 and x minus -5 square root of 2. Just simplifying that a little bit so we don't have the parentheses. Now, these two factors both happen to be real zeros. They're not rational, they're irrational, but they are real. Now, your textbook, for example 1, they give you a couple more three-part example problems. Whereas to find the zeros for a linear problem such as x minus 2, it has 1, 0 at x equals 2. And you can see that from the graph where I have this 1, 0 right here at 2. Now, for example B, where we have x squared minus 6x plus 9 factors into x minus 3 and x minus 3. That's actually considered two separate zeros. Even though it is the 1, 0 of 3 on a graph, it's considered two separate zeros when you're finding all of the zeros of a function. And our graph for that one, since it's a square, it fits this graph here. Now our third degree polynomial function for this problem factors into x plus or minus 2i in x. So it only has one real zero, but then it has the two complex zeros. And our fourth degree polynomial, which could be x squared minus 1 and x squared plus 1, when we factor it the first time, and then we get those four zeros off of that one. And x to the fourth, we can see our two real zeros, and then we have our two complex zeros. Now for another example problem to factor a trinomial. For this one, we're going to use synthetic division. So our possibilities to try out. And I've already put one together and found that -2/3 is a 0. And that leaves us with 3x squared minus 6x plus 12. Now to factor that quadratic, we can use the quadratic formula. And That gives us our 3 zeros of negative 2/3, and 1 plus or minus the square root of 3i. Now my list of linear factors would then be x plus 2/3, and x minus our complex number, and x plus our complex number. Our complex number solutions will always be in conjugate pairs. Since we use the quadratic formula, you're always going to have plus or minus that square root with the complex number. And even if we do not have to use the quadratic formula, and we just have x squared plus 4, our two numbers will be plus or minus the square root of 2pi, so you're still going to have the conjugate pairs. And for our last example problem, we're going to find a 4th degree polynomial with -1, -1, and 3i as zeros. Since 3i has to come in a conjugate pair, that means what I need to multiply together is going to be x plus 1 and x minus 1 for those two zeros, and then x minus 3i and x plus 3i, because I need the conjugate of 3i in there also. And then you just go through all of your Euler and distributive properties and simplify, and you'll find our function